Hello, welcome to my talk. My name is Xin Lu. I'm a graduate student at UC Berkeley. Today, I will be talking about my work, improved pseudorandom generators for AC0 circuits. We start by defining AC0 circuits. They are constant depth Boolean circuits with AND OR gates of unbounded fan-in, as well as bottom NOT gates. Here shows a typical example, where each bottom gate with several literals from X. For example, it can be X1 and not X5 and X7. There are two complexity measures associated with a circuit. First, we define the depth of a circuit and the number of AND/OR alternations. In this example, the depth is 3. We also define the size of the circuit as the number of wires, including input wires. In some settings, people also define the size of a circuit by the number of gates. These two definitions differ by at most a polynomial factor. AC0 is a central computational model that has been studied extensively in complexity theory. Now, people have a fairly good understanding to AC0 circuits. For example, we know strong exponential size lower bounds against AC0. We know how to construct pseudorandom generators for AC0 with short random seed. We know that AC0 is pack learnable with small sample complexity. There are many more applications of AC0 in complexity theory and cryptography. However, for today's talk, we will be focusing on the second topic, that is, construct PRGs for AC0 circuits. Let's define pseudorandom generators. Suppose script C is a class of functions. Let epsilon be a real parameter. An epsilon PRG for script C is a mapping G that maps a short L-bit string into an N-bit string, such that any function in script C cannot distinguish the output of G from uniform. Formally, for every f in C, the probability that f accepts a uniformly random string is epsilon close to the probability that f accepts a string generated by G. We call this parameter L the seed length of the PRG, and epsilon the error of the PRG. There are many good reasons to study pseudorandom generators. First of all, we can use PRG to de-randomize algorithms that are implemented by script C circuits. Constructing PRG is also useful for designing algorithms. In general, an explicit PRG construction for circuit class script C can help us better understand the structure of C. We consider pseudo-randomness for AC0 circuits. This is a central task in complexity theory. People have been working for decades to construct explicit PRGs for AC0 circuits with small error and short seeds. Here, by explicit, we mean there is a polynomial time algorithm, which, given the random seed x, should be able to compute the output g of x efficiently. We want the PRG to have small error, ideally inverse polynomially small of the length n and the size s. We also want the PRG to have a short seed. In particular, we consider the seed length L as a function of other parameters, the input length n, circuit size s, depth d, and error epsilon. We want to minimize the function L. There is a long line of work seeking better and better constructions of PRG for AC0 over the past 30 years. Let us review this line of work first. First of all, by probabilistic method, we know there exists an epsilon error PRG for size S circuit with seed length log S over epsilon, which is independent of the depth D. However, the probabilistic method only promises the existence of such a mapping G. It does not tell us how to find a polynomial time computable one. The first explicit non-trivial PRG for AC0 was given by the Arta and Wiggerson in their seminal work, where they showed a sub-polynomial seed length PRG for constant depth circuits of polynomial size and with inverse polynomial error. They also developed the so-called iterative restriction framework in the same paper. In 1994, Nissan and Wiggerson developed the celebrated hardness to randomness framework. Combining this framework with the correlation bound against AC0 proven by Hastad, one can give a PRG for depth D circuit with seed length roughly log S over epsilon to the power of 2D plus a constant. This is the first PRG for AC0 with polylogarithmic dependence on all parameters. In 2010, a breakthrough result by Braverman shows that any polylog n independent distribution for AC0 circuits. Together with the standard construction of bounded-wise independent distributions, this also gives a PRG with polylog seed length. Braverman's analysis was sharpened by Tao and later by Hashan and Srinivasan, bringing the seed length down to log S to 3D plus a constant times log 1 over epsilon. Remarkably, this is the first PRG with linear dependence on log 1 over epsilon. The Artai-Wigderson framework was revisited by Trevisan Xue and Xue in 2013. Combining the Artai-Wigderson framework with the de-randomized Haastad switching lemma, they gave a PRG with seed length log S over epsilon to the power of d plus a constant. This is the first time that the exponent on log S gets improved to d plus constant. Very recently, there are two incomparable improvements to this Trevisan-Xue result. One is by Cervedo 10, which is based on a de-randomization of Haastad's multi-switching lemma and achieves seed length log S to the power of d plus constant times log 1 over epsilon. The dependence on log 1 over epsilon is linear, and the exponent on log S is d plus a small constant. There is the other improvement by Kelly, which achieves seed length log S over epsilon to the power of d times log n times log S to a constant. The exponent on log S is exactly d. This is indeed remarkable because there is no lower bound barrier. People have observed that a PRG for AC0 with seed length smaller than log S to d minus 1 times log 1 or epsilon would imply new AC0 lower bound that improves Haastad's lower bounds. This would be a breakthrough result in complexity theory because Haastad's lower bound has been the state of the art for more than 30 years. Now we are ready to state our results. We will compare our results with the two incomparable state-of-the-art results, so we list them here for comparison. In this work, we give a new PRG for AC0 circuits with seed length log S to d minus 1 times log S over epsilon times log S. Our PRG improves both of previous works. It achieves the best of both worlds. The dependence on log 1 over epsilon is linear, and the dependence on log S is as small as the one given by Kelly. Also, our seed length does not have the extra log n factor, and the number of log S factors is reduced to 1. All these features push our result extremely close to the lower bound barrier. When epsilon is inverse polynomial small compared to the circuit size S, our seed length is only 1 log S away from the lower bound barrier. It matches the best known PRG for CNFs, which is the depth2 case. Currently, the best known PRG for CNF has seed length log S times log S over epsilon times log S. Set d equal to 2 in our result, we get exactly the same asymptotic expression. Also, if we can shave the log X factor for the CNF PRG, then our construction directly implies PRGs for higher depth circuits without the log S factor. Now let me tell you a little bit about our technique. As we have hinted in the last slide, our result is based on two new technical tools. We introduce them below. The first technical ingredient is a partitioning-based approach to design PRGs. This can be seen as a modification of the Artai-Wigderson iterative restriction framework. This partitioning-based approach is crucial for removing the one last log n factor. The technique itself is simple to describe and is general enough to be applicable to several other computational models. Our second technical contribution is a new de-randomization of Haastad's multi-switching lemma. Essentially, Haastad's switching lemma shows that under a random restriction, a family of DNFs simultaneously simplify with high probability. Our de-randomization shows how to simplify the family of DNFs, but with a pseudo-randomly generated restriction. Now, we give a detailed exposition of the first result. We first give some preliminary knowledge and define some pieces of notation. We consider random restriction, which is a general method to study Boolean functions. Roughly speaking, Given a function f, random restriction works by randomly choosing and fixing a subset of input bits to f. Then we study the behavior of f on the remaining input bits. We define a notation for this. For a set lambda and two binary strings x, y, define lambda of xy as a new n-bit binary string as follows. In particular, for each coordinate I, if I is not in the set lambda, we set the ith bit of lambda xy as xi, otherwise we set it as yi. We define the restriction of f by a pair lambda x as the following new function. Roughly speaking, this is fixing all but the lambda part of the input, and then consider how f depends on the unfixed bits. We are ready to show the template to construct PRGs. Let C sub Gao to be a circuit class for which we want to construct a PRG. Suppose we have identified a simpler class C simple and a pseudo-random distribution X that can epsilon force C simple. Also, suppose we have a distribution Y and a simplified under restriction lemma looks like following. Suppose lambda is a k-wise independent subset such that each element I belongs to lambda with probability P. In the following, we will refer to this property as P marginal. Then, if we shoot C Gauss circuit with a random restriction given by lambda and Y, the circuit simplifies to a C simple circuit with probability 1 minus epsilon. This is why we call this lemma a simplified under restriction lemma. Having prepared all this, we construct a pseudo-random distribution. First, we sample H, which is a k-wise independent hash function that maps n coordinates into W buckets. We also sample x1, x2 up to xw to be W independent copies of x, and we also sample a single copy of y. Then we compute a string B by this formula. Intuitively, we partition the n coordinates into W buckets by the hash function H. Then we fill in each bucket with independent copies of x and combine these W pieces together and XOR it with the string y. Here, this XOR and AND should be understood as bitwise XOR and bitwise AND. We want to show that B follows C Gauss circuits. So, fix C to be a C Gauss circuit that we wish to fool. Consider the average of CB. Recall the definition of B. Consider observing all but the x1 part in B first. Mathematically, this is just switching expectation orders. This can also be interpreted as hitting C with a restriction lambda z, where lambda is given by H inverse of 1, and z contains all but the x1 and x inverse 1 part in this B string. Given the random restriction, we want to apply the simplified under restriction lemma. We can find that H inverse 1 is indeed a k-wise independent and a P marginal subset of n elements. Moreover, if this C can be equally useful as Y, then we may hope that the restricted circuit is in C simple with very high probability. If C does simplify, then it cannot distinguish X1 from a uniform string. So we can replace X1 with a uniform string and get a related distribution B1. We have just shown that the expectation of C on B and on B1 are 2 epsilon close. We also give some intuition about why this Z should be equally useful as Y. Note that Z is obtained by just flipping some bits in Y, which is independent of Y itself. So intuitively, flipping a fixed set of input bits do not break typical pseudo-randomness properties, such as k-wise independence and low biasness. Now, we can do the same argument for this x2 part, namely, we define B2, which is obtained by replacing x1 in the B1 with a uniform string. We can show that C of B1 is at 2 epsilon close to C of B2. Continue, we use a hybrid argument. We can define a series of distributions, B3 up to BW, where we replace these xi's by uniform strings one by one. Finally, we can show that C of B is 2wi epsilon close to C of B 2w. It is easy to see that BW is just uniform string. So we can conclude that B does for Seagull with a slightly larger error 2w epsilon. Now let's consider the seed length. The seed length to sample B is the sum of three terms. The first term is W independent copies of X. Recall W equals 1 over P, where P is from the simplifying under restriction lemma. The second term is a single copy of Y. Y is also used for the simplifying under restriction lemma. The last term is a k-wise independent hash function, which requires O of k log n bits. So both 1 over P and K depend on the quality of the lemma. By this, we mean the following. Recall the statement of the lemma. In this lemma, if we can make K smaller or make this P larger, and let the result probability lower bound still holds, then potentially we can reduce the seed length of the PRG. We also remark that the first term, that W times the seed of X, is usually the dominating term. Next, we describe how we apply this technique to AC0 circuits. We will identify Seagull as depth D size S AC0 circuits, the target circuit class we want to fool. We identify C simple as depth D minus 1 size S squared circuits. So when we simplify a depth D circuit, we are trying to reduce its steps by 1. We will prove a de-randomized version of Hastad's multi-switching lemma. But for this talk, it suffices to know that this lemma works with parameter 1 over P and K being log S. The seed length for Y is roughly log squared S times log S over epsilon times log S. In fact, we are just taking Y from a PRG for CNF with a relatively small error. Then we can write seed length for the depth D circuit as a function of that for depth D minus 1 circuit plus 1 extra term due to the string Y. If we assume D is at least 3, then this Y part would not be the bottleneck. Therefore, the depth D circuit would have seed length longer than the depth D minus 1 circuit PRG by log S. For depth 2, the best known PRG for CNF has seed length log S times log S over epsilon times log S. We use it as our starting point. For every constant D, we can construct a PRG with seed length log S to D minus 1 times log S over epsilon times log S. This is the main claim of this paper. It is worthwhile to compare our approach with the standard Artai-Wigderson framework. We briefly review the Artai-Wigderson below. For the Artai-Wigderson framework, the setup is similar. We need to identify the target circuit class Seagull and the simpler class C simple and a PRG for C simple. A difference in Artai-Wigderson is that it only needs a partially de-randomized simplified under restriction lemma. Only the set lambda needs to be pseudo-random. The restricted string can be uniformly random. Set a parameter R as log n over P. We prepare R k-wise independent and P marginal subsets denoted by T1 up to Tr. Also let X1 up to Xr be R independent copies of X. Then the PRG outputs something like the following. Intuitively, this is iteratively fixing bits. In the first round, we fix the T1 part by X1. After that, we will keep T1 part always fixed and fill in remaining parts. In general, in the Tth round, the PRG fixes the coordinates given by the T set minus the previous sets. Each round fixes roughly P fraction of currently unfixed variables. So we need log n over P rounds to cover all the coordinates with high probability. Here's something magic about the construction. When we use the construction and we want to prove the indistinguishability, we can actually assume the unfixed part are truly random. This is why we only need a partially de-randomized simplification lemma. Let us compare the new approach with the standard Archive-Wigson approach. In this partitioning approach, we use a hash function to perfectly partition the input bits. There is no waste of randomness. However, the downside of the approach is that we need a fully derandomized simplification lemma. The iterative restriction, on the other hand, only needs a partially derandomized simplification lemma. However, it loses a log n factor in the construction because it needs to iterate for log n over p rounds. Let me add one more quick remarks about the partitioning restriction. The partitioning restriction is fairly general. The currently best known PRG for sparse F2 polynomials and small size De Morgan formulae use the Archive-Wigson framework. We can apply a partitioning restriction in these cases and shave a log n factor in the seed length of PRGs. However, these PRGs have a very long seed length. Therefore, improving a log n factor is not as significant as for AC0 circuits. We also note that the current best PRGs for arbitrary order read-once branching programs also use iterative restrictions, but the proof is mostly Fourier analytic, and the partitioning approach does not directly apply. However, the log n factor incurred by the iterative restriction is indeed crucial for this model. It is the difference between log cubed n versus log squared n, or log squared n versus log n. As we know, if we can have a log n seed PRG for polynomial with ROBP, then RL would equal to L. Therefore, it is natural to ask if we can use the partitioning approach to replace the iterative restriction and shave this extra log n factor. Due to time limits, we only quickly go over our second technical contribution. So roughly speaking, our derandomization of Haastad's multi-switching lemma improves on two previous results and achieves a best of both worlds result. Our derandomization of the multi-switching lemma simplifies previous proofs and gives some new insight about DNFs and random restrictions. So for interested readers, we highly recommend reading the paper for the detail. We conclude with some open questions. First, the immediate question would be further reducing the seed length. First, if we want to shave the log x factor, one option is by a Fourier analytic conjecture called Manson's conjecture. In particular, this conjecture implies that we can shave log x factor for the CNF PRG, which further implies shaving log x for all constant F circuits. The second direction is to improve the dependence on log s when epsilon is relatively large. And then more open-ended question, we ask if we can break the log s to d-1 times log 1 or epsilon barrier. We believe this shouldn't be impossible. Third, we ask if we can use partitioning restriction to design PRGs for other models. For example, shaving a log n factor in the PRG for branching programs would be a major advance in derandomization of small space computation. Finally, can we find more applications of new derandomized multi-switching lemma? Thank you for your attention.